Let's talk more about receptors that sense neurotransmitter. We're going to divide the receptors into two groups. One of the groups is gated ion channels. Opening ion channels, like sodium channels, causes a voltage change across the membrane. By causing a voltage change across the membrane, we get an instant on-off reaction to a neurotransmitter. So this is how your neuromuscular junction works. When your muscles sense acetylcholine by the nicotinic receptor, which opens a sodium channel, and sodium comes rushing across the membrane, causing a voltage change. Once those sodium channels shut, the signal is turned off instantly. So again, by opening an ion channel like a sodium channel, this causes a voltage change across the membrane and gives the neurotransmitter instantaneous on-off effect on the postsynaptic membrane. So here is my neurotransmitter. Maybe it's acetylcholine, and this is a nicotinic receptor at the neuromuscular junction, this being the postsynaptic membrane. And the neurotransmitter here activates the receptor, opening a ligand-gated ion channel, ligand as in some chemical like the neurotransmitter, gate as in open and shut, ion as in sodium channel. Sodium can't move across the membrane on its own. Sodium needs a channel to move through the membrane. So here the neurotransmitter is activated ligand-gated ion channel, and by moving that positive charge across the membrane, we've caused an instantaneous change in the voltage of that membrane. Some of these ion channels are voltage-gated as well. Voltage-gated ion channels are activated in response to voltage change. Instead of some chemical causing the change, a voltage change across the membrane causes the gated channel to open. And again, this gives us instantaneous on and off communication with the postsynaptic membrane. Well, not everything we want is this instantaneous on-off. That works for fine muscle movement like your fingers. When you control those muscles, you want them to start and stop instantaneously, and so that's why that's controlled with gated ion channels. Second messenger activation gives us a slower change and allows these metabolic changes to occur. And so when your sympathetic neuron speeds up the heart, or when your parasympathetic neuron, your vagus nerve, slows the heart down, that's not this instantaneous on-off, fast, slow. Your heart doesn't work that way. Sympathetic nervous system speeds your heart up. It's going to keep racing for quite a while, and all sorts of metabolic changes need to occur in the cardiac muscle to accommodate this increased oxygen demand, increased metabolism. When we read about the autonomic nervous system communicating with organs, smooth muscle, we're usually using second messenger systems. So here a neurotransmitter is activating a receptor, activating a G-coupling protein. You can read all about that. And here we've activated an enzyme called adenylyl cyclase. And adenylyl cyclase will convert ATP, adenosine triphosphate, into cyclic AMP. And cyclic AMP is our second messenger. And so when this agonist, when this neurotransmitter activates a receptor that activates adenylyl cyclase, then we'll end up with increased cyclic AMP levels. So you might have a pharmacology reference book that talks about this drug raising cyclic AMP levels, or maybe the drug decreases cyclic AMP levels. Well, cyclic AMP inside of the cell has all sorts of regulatory functions. So cyclic AMP can activate many different regulatory proteins. Receptor regulation, metabolism regulation, DNA regulation. There's all sorts of things that cyclic AMP does. Of course, cyclic AMP can activate or deactivate all sorts of regulatory proteins. Cyclic AMP is a second messenger, and you'll see cyclic GMP used as a second messenger as well. Phosphodiesterase breaks down cyclic AMP. The end product is called 5' AMP. Well, phosphodiesterase is inhibited by various xanthines. One of them is caffeine, and so there's my phosphodiesterase, and it has a caffeine receptor on it. And so there's my 2 happy cups of coffee in the morning, and those happy cups of coffee block phosphodiesterase. So phosphodiesterase is inhibited by xanthines. You might read about xanthines that inhibit phosphodiesterase, and my favorite is coffee, particularly 2 cups of coffee. And what that does, by blocking phosphodiesterase, we're raising cyclic AMP levels. All right, well, think about it. We've now discussed two ways to raise cyclic AMP levels. Here, we used caffeine to raise cyclic AMP levels. And here we used a neurotransmitter to activate adenylyl cyclase to raise cyclic AMP levels. So we can divide the receptors into ionotropic, which means some kind of gated ion channel, and metabotropic, meaning it activates some kind of second messenger system.